So we have 2 talks more, and the next speaker is Sarah. So Sarah will give us a detailed overview of spin polarized spectra and spin polarized nonadiabatic couplings. And as you have seen before, we look on spectra first and coupling second because they have some similarity in equations how they are formulated. Okay. Sarah, please go ahead.
Thank you, Dr. Kin. I think everybody explained the work that I'm going to present, so I will quickly show it. So I'm going to explain how to plot the absorption spectra for different spin components in a case of spin polarized. So the file that we require for plotting the absorption spectra are postcard, key points, outcard, waveguard, postcard for the for the optimized geometry. Then the first step is we need to create a file as others explained, input overlap, and set the range of orbital energy that we want. We repeat it twice because we have 2 spins, spin up and spin down, and also we need to specify a placeholder number 1 at the last line. Then we need to run this executable in order to extract the energy pop files for the spin up and spin down. Next step is the actually run these 2 executables to see the transitions for the spin up and spin down components, and it will gives us the OS strengths and OS strengths down files. So it's better to maybe rename the name of the OS strengths file to OS strengths up. Maybe it's kind of easier, but it's a personal choice. Then we need to extract the occupied to unoccupied transitions from 1 to 0 from each of the OS strengths files and put it in another file called OS up and OS down. So here, after copy and pasting the OS strengths up file into the OS up, we need to specify the number of transitions for this component or the alpha component, and then execute the following code. So in this code, it requires number of transitions, which I said we need to count the number of lines of the OS strength file, and then the range of energy that we want to plot the absorption spectra. In this case, I chose just 0 to 10 electron volt. The width of each line, as well as the number of the HOMO orbital. Then we can use the GNU plot command to generate the absorption spectra as a function of energy and as a function of the wavelength. And then by using the last comment, you can just convert the file to the PDF format, and here you can see this is the absorption spectra for the alpha component. For the beta component, everything is the same. Just you need to copy and paste OS down, as I explained before, into the OS strength file, and again execute that command and count number of the each line OS strength file lines, and then using and enter the number of HOMO again for the beta component, and again using the GNU plot command, you can generate these plots for the beta component. And then for the non-adiabatic coupling calculation, as London, Hadassah, and Amara explained, this is the case for the Mm. I am explaining for the spin polarized case. So after heating and the molecular dynamics, you need to copy outcar, key point, postcar, and podcar, as well as the input overlap and the incar, Cori.sh and the BS script file into another directory, maybe nonadiabatic directory, maybe, and then execute the following command again to generate the different snapshots or the files that's already explained by Adam, maybe the P00, something like that. Those files you can generate with this executable. And then also, as others explained, you should notice that the postcard file is in the WASP4 version. And then you need to, as Amara explained, this is the BS script provided by Dr. Han. These are, it says that, for example, create a directory called up and another directory for the spin down. And you can here specify the range of energy and or the range of time step that you require that you want. And here the top, this part is for the spin up and this part is for the spin down. So it's automatically generate the energy pop, extract the energy pop files for the spin up and spin down, and do the calculations for each spin component. So if everything it goes well, you can see the coupling files generated in each directory for spin up and spin down. So on these, the data for different spin components are kind of different from each other. They are not the same. So that's it.
Okay, please join me in thanking Sarah.
Thank you.
So, any questions in person, online, or in the chat line?
So for the chat, you ask why input overlap has 5 lines instead of 3. So I said that because we have 2 spin components, spin up and spin down. So 2 of them are for the spin up and 2 of them are for spin down. And the last line is for the placeholder. And another question, which system is...
How to say that homo for spin up and homo for spin down may not be equal?
Yes.
Yeah, thank you.
Yeah, here as I said, for example, this one is for the spin down, it is 194, while for the spin up, it is 195. So another question is, which system is used as an example? Just curiosity. It's the Clay system for the n up down equal to 1.
Thank you.
Yeah.
Any more questions? Sir, I'm expressing curiosity in a couple of other questions.
In the chat?
Yes.
Okay. In which situations one needs spin polarized calculation and one can make the I think it depends on the type of material and the system. For example, when we have the transition metal atoms, maybe we need the spin polarized calculation.
Okay, so you want to say that if there are unpaired electrons, then one needs spin polarized?
I guess.
Okay, and then the next question, when spin polarized is insufficient and one needs something upgraded, like when does one need spin orbit coupling?
I'm not sure. Maybe when I think it depends on the accuracy that we want from the system. For example, when for the spin orbit coupling calculation, it kind of maybe it's more precise and more expensive maybe.
Which process is forbidden in spin polarized calculations? And Hanman, please try to think about it. If you do not want to answer, if you don't have answer, do not reply, but just try to think. And it's a question to everyone who deals with transition metals. If we all fail to answer, David likely will provide an answer. He speaks next, but which not quantitative, not quantitative improvement of precision, which qualitative process is not available in spin polarized calculations?
The kind of the interaction between a spin and the orbital, something like this, yeah?
Right. So let me show.
You mean the angle of the maybe electrons? It's just maybe up and down. Maybe in the spin orbit it has another angle, maybe 45 degrees, something like this.
So, Herman, what is the main excitation of your system? And I know also that Adam knows the answer. So, what happens to the spin multiplicity when you go from your ground state to excited state in your manganese dome?
Different splitting happen.
Do you have the same spin polarization before and after excitation, or it changes?
It changes.
Okay. Sarah, does it give a hint? So in your publication, you separately considered low spin, intermediate spin, and high spin.
Yes.
And the calculations that you did were independent. There were no transitions between low and high spin. And spin orbit coupling does allow natural conversion between them.
Mm-hmm.
Adam, do you want to add anything? Triplet. Okay. Okay, yeah, thank you.
I see. Thank you.
There was a question from Aaron in the chat room.
What to do with all energy pop and OS files generated? I'm not sure about the energy pop files, what we do, but for the calculation that we did, we just used the energy pop that actually generated from the geometry optimization. So maybe here I saw that in this file, the energy pop here, it says remove this file. I'm not sure. It's a good question. I'm not sure about the response for this question. The OS file generated. And
Sarah, would you please show the list of files generated maybe in the next slide?
Yes, here.
Yes. So here there are oscillator strengths computed at each time step.
Yes.
And I believe Aaron is asking, why do we need them? Can we get anything good out of them?
You mean for the plotting the non-adiabatic calculation, kind of the plot that we had, for example, from HUMO minus 17 to LUMO plus something, the different transition, kind of the evolution of the energy in the time, or the evolution or the dissipation of the energy in the time, maybe using that Redfield tensile energy. It kind of needs this file. I'm not sure how to explain it.
Yeah, thank you. Aaron, are you satisfied, or you want to hear more?
I guess I would say that like within the group, there's no standard way, but like usually a good practice is to like take the average, at least for the energy pops anyways, to like average those, since like each one of those files is one step from the molecular dynamics. And usually it's like what you see in experiment is an average value. So you can take the average of all the energy pop files, and you can either take the average of all the OS strength files or just combine them into one big file and plot the spectra that way.
Yeah.
So those are
exactly.
two possible things to do with all these files.
Mm-hmm. Yeah, exactly, because our resources kind of is limited, so we run the simulation for kind of limited femtosecond, and then we may predict how the simulation or how the system goes, the energy of the system, for example, goes by using that Redfield tensor equation. So it needs these OS strength files, or the, as you said, or by averaging from these energy pop files. Am I correct, Dr. Dr. Klim?
There is additional ways to do Redfield dynamics. Plus, there are some additional methods based on this data that you have made it in 3 views.
Yeah.
Okay. More questions to Sarah? Questions 1, questions 2, questions 3. Thank you very, very much. It's really good.
Thank you.